In North Dakota, 3,500 kilometers from Mexico, fish seem to have died, with asteroid glass stuck in their gills. They weren't just dead things lying around afterward. They were, apparently, alive, breathing river water, while molten droplets from the Yucatan were raining out of the sky. A few minutes or hours later, the river surged like somebody had shaken the continent. Farther south, the impact had punched a crater about 200 kilometers wide into a shallow tropical sea. But frankly, the asteroid didn't need to blow up every dinosaur. It only needed to make the sun stop working for them. To be annoyingly precise, the dinosaurs that vanished were the non-avian dinosaurs, the tyrannosaurs, ceratopsians, hadrosaurs, ankylosaurs, and all the other large land animals people usually mean. Birds are living dinosaurs, which is a technicality that happens to be completely true. So the story isn't that dinosaurs disappeared entirely, it's that almost every dinosaur lineage on land failed, while one small, strange branch carried on. Just before the impact, the last Cretaceous world was not a wasteland. In spring, hadrosaurs nested in colonies. Triceratops grazed through low vegetation. Insects moved through flowering plants, and rivers were full of paddlefish and sturgeon filtering whatever the water brought them. It was, in other words, a functioning planet, which is precisely why breaking it was so efficient. The impactor itself was roughly 12 kilometers wide, which is large, but not magically large. The especially grim detail is where it landed. The Yucatan platform was packed with carbonate rocks, sulfur-rich evaporites, and organic-rich sediments that could turn into soot. It wasn't just a target, it was a chemical inventory. Modeling suggests the asteroid struck steeply, perhaps close to 60 degrees, which is a rather unfortunate angle if your goal is keeping climate poisons out of the sky. A shallower hit might have thrown less material upward. This one was more like stabbing the atmosphere from below. Near the crater, of course, subtlety was not really involved. Rock melted, seafloor vaporized, and the crust rebounded into a peak ring like Earth briefly forgot it was solid. Then the ejecta went above the atmosphere, fell back around the planet, and heated the air as it returned. For dinosaurs in North America, the first sign may not have been a visible crater at all. It may have been the ground rolling under their feet. Birds would have launched from trees, nests would have shaken, and rivers would have started behaving less like rivers than bathtubs in an earthquake. At Tanis, the deposit looks like that kind of violence preserved in sediment. Not a neat ocean tsunami, necessarily, but a seiche, an inland surge triggered by seismic waves crossing the continent. The fish were feeding when the glass arrived. Tiny spherules fell into the water. The fish pulled them across their gills, and then the wave buried the whole awful moment. Some evidence even suggests the impact happened in boreal spring, which is a genuinely nasty season for catastrophe. Animals were nesting, growing, migrating, laying eggs, and generally making the sort of biological commitments that assume tomorrow will be normal. The crater itself later gave up an almost indecently direct record of day one. In 2016, scientists drilled into Chicxulub's peak ring, and one core held about 130 meters of impact melt and broken rock deposited almost immediately. Above that was less than a meter of carbonate laid down over weeks to years. The same core contained charcoal, but was surprisingly poor in sulfur minerals, which fits the rather bleak idea that the sulfur didn't stay in the rock. It went into the atmosphere. That atmospheric part is the real extinction story. The blast killed locally. The sky killed globally. Sulfur aerosols, dust, and soot reached the stratosphere, where rain couldn't simply wash them out. Some soot estimates are enormous, with black carbon from the target rock reaching around 10 to the 15th grams. One model found sunlight could drop by 80 to 85%, while another sulfur model cooled the planet by more than 20 degrees Celsius. The exact numbers vary because climate models are models, not security camera footage, but the basic shape is not subtle. Less sunlight reached leaves, less photosynthesis happened, and the green base of the land food web started to fail. For a triceratops, this is not an abstract climate problem. A body that large is basically a walking demand for plant productivity. If fresh growth stops, herbivores start spending calories looking for calories. That works poorly. Then the carnivores inherit the same problem one step later. A tyrannosaur can be very powerful and still be attached to the same food web as everyone else. Power doesn't help much when the prey base is disappearing. This is why the asteroid story is less satisfying and more disturbing than the movie version. Most animals weren't dramatically vaporized. They were forced into a world where eating became considerably harder every day. The ocean, meanwhile, had its own version of the same failure. Plankton need light, and plankton feed the small animals, which feed fish, which feed larger predators. When the surface darkened, the marine food web didn't politely pause. It thinned, then broke unevenly. Foraminifera chemistry suggests surface oceans acidified rapidly by about a quarter of a pH unit. That sounds small until you remember pH is not a friendly scale. The biological carbon pump stayed disrupted for hundreds of thousands of years, and probably more than 1 million. Ammonites, which had survived a frankly impressive amount of earlier planetary nonsense, didn't make it through this one. Nor did mosasaurs or plesiosaurs or a great deal of the open ocean world that depended on light arriving on schedule. On land, the question for decades was whether dinosaurs were already fading before the impact. Some groups may have been under pressure, and ecosystems were not identical everywhere. But the clean version, where dinosaurs simply shuffled off before the asteroid arrived, doesn't fit very well. In Hell Creek, a ceratopsian browhorn was found just 13 centimeters below the boundary layer. 13 centimeters of rock is not a long farewell. The global evidence for the impact began, rather wonderfully, with a thin clay seam in Italy. Walter Alvarez was studying rocks near Gubbio, where Cretaceous limestone abruptly gives way to Paleogene limestone. His father, Luis Alvarez, suggested measuring iridium, a metal rare in Earth's crust but comparatively common in meteorites. Frank Asaro and Helen Michel did the lab work, and in 1980, the group reported anomalously high iridium at the boundary. That was the first serious fingerprint of something extraterrestrial. The crater took longer to connect. Glenn Penfield and Antonio Camargo had seen a huge circular gravity and magnetic anomaly under the Yucatan. It was sitting there, under younger sediment, being extremely obvious in the way buried craters aren't. By 1991, Chicxulub was identified as the likely impact structure. High-precision dating now puts the boundary around 66.043 million years ago, with the impact essentially simultaneous with the extinction on geologic timescales. By 2010, a large review pulled together the crater, iridium, shocked minerals, ejecta, tsunami deposits, and abrupt fossil losses. The asteroid was no longer just a dramatic suggestion. It was the main explanation scientists had to account for. Volcanoes still complicate the story, because Earth apparently felt this moment needed footnotes. The Deccan traps in India were erupting around roughly the same time, and those eruptions likely stressed climate and ecosystems. But habitat modeling suggests Deccan volcanism alone couldn't erase suitable dinosaur habitat globally. The asteroid could. There is even an awkward possibility that volcanic carbon dioxide warmed the planet somewhat, partly softening the coldest edge of the impact winter. Nature is not obligated to keep its disasters thematically clean. The truly selective part was survival. Big, specialized, green food web animals did badly. Small animals with flexible diets did better. Burrowing helped. Low metabolism helped. Living in freshwater helped because many freshwater systems can run for a while on detritus. Detritus is a polite scientific word for leftovers, rot, and the edible remains of a ruined world. A crocodilian lying half-buried in a riverbank didn't need a thriving forest tomorrow morning. It could wait, eat carrion, and let the water hide some of the catastrophe. Bird survival was also not a simple matter of having feathers. Many bird-like dinosaurs died. Tree-dwelling birds likely suffered badly when forests collapsed. Forests didn't just get scorched. In many places, they vanished as functioning habitats. The birds that made it through may have been small ground dwellers with beaks, because seeds can sit there being food long after leaves have stopped being leaves. It's a bleakly practical advantage. A recent plankton model found something similar in the sea. Small, economical organisms had better odds than large, energy-hungry ones. The extinction was not a contest of strength. It was a contest of overhead. After the worst darkness eased, the planet did not reset like a machine. Marine carbon cycling stayed strange for an immense stretch of time. Forests had to rebuild from survivors. Mammals began expanding into spaces that had been occupied by dinosaurs for ages. Every city, farm, road, and person now exists in the aftermath of that opening, which is a slightly uncomfortable debt to owe a rock from space. The non-avian dinosaurs didn't lose because they were weak. They lost because the planet's power source flickered, and when the sunlight came back, the world belonged to the animals that could survive in the dark.